you just start out by telling us a little bit about how you started working in the machine learning space and also just your path to the present?
Sure. So I, prior to joining Lawrence Berkeley National Lab as a postdoc, I worked on computational statistics methodology development at the Basque Center for Applied Mathematics, Beckham, in Spain. And my main research was focused on developing advanced Monte Carlo methods for statistical sampling, particularly in the context of Bayesian inference. I worked on projects ranging from finance, reservoir simulation, molecular simulation. So I hold degrees in applied mathematics and financial mathematics.
Okay.
So when I joined LBNL, I started working in the field of synthetic biology. So this was my first encounter with the field, and I became absolutely fascinated by it. So now I work as a data scientist within both the Agile Biofoundry and the Joint Bioenergy Institute. And I work on the development of machine learning based algorithms and tools with scientific software development um, for predicting outcomes of bioengineering. Um, so I actually started working on particular machine learning tools when I joined LBNL. Before that, I worked more on the algorithm development using Monte Carlo approaches and within the Bayesian inference context.
You mentioned that you, prior to working on this project, hadn't worked specifically on machine learning. And so I'm curious to hear your thoughts about how you got involved in that space and how you learned. And also, I guess, a related question, like when you're talking to people now who are interested in learning more about this area, like other students or postdocs or faculty members, like how do you recommend they start out?
Mhm. Yeah, so in my opinion, I think the best background to have for these types um, of topics is to have a mathematical or engineering background for the best understanding of abstract concepts. To be aware that assumptions do hold. For example, in a simple case, we should know if should be aware if our data is following a Gaussian distribution, for example, if a particular model has this assumption. So for these types of concepts, statistics and probability classes are a great start. Also, linear algebra. Another important thing would be to pick up our programming language and
Yeah.
learn. Doesn't have to be anyone specific, although we are extensively using Python nowadays. I actually started with MATLAB, R, C, and I actually started working with Python when I joined LBNL. But I think that's a great way to have the mindset of and knowledge on how to communicate with the program, and what would be the assumptions. When it comes to more applied side on how to combine machine learning with synthetic biology, we actually published an extensive review last year on the review of machine learning for metabolic
About
engineering.
engineering. Yeah.
Um, Also, a great thing would be to check out some course, and there are a number of them available, but maybe not going straight away into the details of all the methods. Maybe just to see what's out there, what's available, what kind of tools. But my advice to really go into the details would be to learn by doing. So if there is, that's at least how I approached. If you have a project to work on or a data set, it doesn't have to be um, um, very extensive or related to um, or a real case scenario, which is scarce in any case. But choose a project to work on, and then you will find out the solutions to problems that you would encounter on the way. And as well, during alongside, you would be checking out different tutorials of the tools and read the documentation the
Mhm.
tools, for example, such as scikit-learn or TensorFlow, Keras. Those are the most commonly used tools nowadays.
So sometimes people have experimental data or other things that they want to work with, but if they are interested in kind of pulling a data set from a paper or somewhere on the internet, like, do you have recommendations on like what interesting places that would be to look for data that people could use if they want to just try out some of these methods on relevant data sets?
I mean, because it's a real struggle, at least
Yeah.
in our field. So when I started, we yes, I mean, we had some in-house studies, and then getting to those data and form of those
Yeah.
data, uh, at that time they were not as standardized, so there are a lot of
Hmm.
challenges there. So it's not as um, ideal as in other fields to find
Right.
good data sets. However, we are providing, alongside with the R tool in our repository, we are providing some data sets that people can use and play with, use R tool or some other tools. So that might be one.
Yeah. So, in your opinion, are there projects that just aren't a good fit for machine learning? Like, if people are curious about whether their research would benefit from using these tools, do you have advice about what kind of key ingredients need to be in place for this type of project to be successful?
Yeah. So it is often the case in metabolic engineering that we have omics data sets that display tens of thousands of features or input variables, but only for a small number of instances. So these are
Mm-hmm.
so-called short and fat training data. And the problem is that if we would have applied machine learning, the model would most likely be underfit, and it will have very poor predictive accuracy. So
Right.
here we are entering in the dangers of the curse of dimensionality, which means that the amount of data needed to support results in a statistically sound fashion grows exponentially with dimensionality. So alternatively, we could try to, for these types of data, we could try to apply feature selection methods provided by unsupervised learning and reduce the um, input space. But if that's not enough, we just need to gather more data. And it might happen that the result of our um, model predictions would not be very different than just the random choice.
Mm-hmm. Okay.
And more generally, um, regarding the infrastructure and the planning that should take place to make sure we could apply machine learning, I would emphasize that we need high throughput data collection.
Mm-hmm.
We would need the data structuring, data standards, ontologies, databases.
Mm-hmm.
Um, Once we have that in place and we have nice data sets to work with, we would proceed with data pre-processing, some cleaning, outlier detection.
Right.
We normally then just try some maybe simple methods without much tuning and going into complex types of models.
Mm-hmm.
And at the last stage, we can apply some more sophisticated models, such as deep learning ones.
Mm-hmm.
And when it comes to some more practical considerations of for implementing machine learning, so we in our review we provide an extensive list of steps that should be considered when leveraging experimental data with machine learning based tools. So I'm going to mention just a few of them. For example, a lot of care should be given and time invested at the very beginning before any experiment is done in terms of planning. So we really have to know what are we trying to optimize, what is our objective of this study,
Mm-hmm.
and then what are the inputs that would actually affect these outcomes, and
Right.
are these inputs actually actionable, can we
Mm-hmm.
measure them? Once we
Mm-hmm.
provide recommendations for those inputs, can we actually then test them and build them later on? um, Other thing is really to create consistent protocols
Mhm.
We generate repeatable data, and we should be aware of hidden variables in the process.
Mhm.
For example, some of the steps in the protocols might be omitted by one person, um, and not by another one, and so on.
Right.
Data
Uh,
standardization and so on. Um, and regarding people or skills involved, I believe that the group would benefit from having a computational or a machine learning expert
mhm.
either on the team or as a collaborator.